This video demonstrates Polar's tracking application, which is based on fuzzy logic. As with all tracking applications, the essential qualities are twofold: the ability to identify the object to be tracked, and of course, the ability to thereafter track that object. In step 1, the motion tracking application first needs to receive the input source. This is either a live video feed or a pre-recorded video. Once received, the signal is further split into frames. Step 2 involves the determination of interframe correlations. These results are then sent to the threshold discriminator, which determines any interframe differences. In step 3, key information regarding any intraframe motion is identified and mathematical determinations are made about the object's movement. The input data undergoes a simultaneous statistical filtration process in order to obtain an accurate picture of the motion. The information collected and analyzed in step 3 is displayed on screen in the form of an interest area. This is represented by the green box that you can see. The object trajectory is indicated by the red line. The contours of any moving object on the screen, here the tennis ball and the two players, are set against a black background to allow for an easy identification of all moving objects. In this video, I'd like to demonstrate the algorithm of OpenCV. The first window displays how OpenCV defines the difference between two frames. In the next step, it transfers the image in the grayscale to reduce the amount of data needed for processing. In the next step, it blurs the image for the convenience of subsequent contouring. Then it creates the binary image for the blurred image to be more clear. In the last step, it inflates the contours into large blocks to further combine them into one moving object. As you can see, there is a selection of moving sets of elements that are not always identified when their movement is more dynamic. You can even observe the split of the contours of the object as if there are two balls. This indicates the functioning inefficiency. OpenCV algorithm is too slow to follow the ball. It is also important to highlight that Polar's application based on fuzzy logic defines a common area as a rectangle, where all the movement is happening, whereas OpenCV splits the elements into smaller ones, which is further combined into one area. This process requires additional computation. In this section of the video, we'd like to demonstrate the core functionality of Polar's motion function, which is an essential part of video analytic and surveillance systems. Here, the algorithm determines the main object, in this case, a person, and the trajectory of the movement is tracked by the red line. We will further describe each element of the algorithm step by step. These steps are all interconnected in a specific functional sequence that ultimately results in Polar's solution. The first step is to use the motion detection algorithm, which is based on fuzzy logic, in order to determine the area within the frame that undergoes motion. The algorithm then makes correlations between adjacent frames of the video stream being analyzed. These correlation values allow the algorithm to determine the contours of the moving object. When an object is no longer moving, the contour silhouette also disappears. For example, we can see how a person throws a marker on the table and clearly identify those parts of the person's body that are moving, his hands, arms, etc., as well as the marker as it rolls along the tabletop. This stage is designed to identify motion within video frames. The second step is to use the motion detection algorithm based on fuzzy logic to compare the current object and a static picture. On the screen, you can see the original image, which is the last frame from the video stream, and the image processed using this algorithm. The comparison is not between adjacent frames, but with the current frame and the frame where there is no person at all. You can see sharper objects filled with color with sharper edges. This algorithm is used to search for static objects or to correct moving objects if they stop. The third stage demonstrates how the algorithm constructs a contour skeleton. The algorithm draws correlations between colors within a given frame. This makes it possible to define clear edges with a high degree of accuracy. On the upper screen, you can see such correlations being made with respect to a moving object within a video feed. The contours of the object are clearly defined, as are the contours of the room and the other objects that are present within the frame. On the second screen, we are looking at a static snapshot of the same room. The contours are easily identified, and the algorithm allows the user to eliminate those objects which the user considers to be noise. The final, fourth stage, is a demonstration of removing noise from motion detection on a static object when correlating with a static skeleton. As you can see, we have two main images: motion detection image with highlighted motion, and an image based on the static algorithm for correlating the original image. The observed edges can affect the definition and vision of the object. These contours can be removed when correlating a given image and skeleton correlation. With these actions, most noise goes away and the object remains in the picture. To form a comprehensive understanding, I'd like to demonstrate how OpenCV detects motion. The first step is to determine the absolute difference relative to the original image. The second step is to bring this difference to the grayscale to increase the processing speed. The third step is to blur the image itself to establish the contours. The fourth step is to bring the blurry image into binary mask so that the contours become clearer. The fifth step is to inflate the contours to create a closed loop. The sixth step is to isolate the contours when objects are moving. Each of them can be highlighted in squares separately. The problem here is that the image itself can scatter into a larger number of individual contours. This issue will require additional algorithmic power to connect all the elements to fix the general area of motion. Due to the inflated contour, the selection does not always occur where the object is. To find out more about Polaris motion tracking algorithm or to get in touch with the team generally, please contact either Peter or Daniel via email provided on the screen. We would also be more than happy to work with your team to coordinate a live demo to show you how Polaris solution can reduce latency, minimize operating costs, and increase efficiency for your organization.